Good afternoon, everyone. I'm Zhiyue from Tsinghua University. Today, I'm going to introduce our work, StreamCache, revisiting page cache for file scanning on fast storage devices. I'm going to introduce this work in the following parts. They are the background and motivation, design and techniques, evaluation and conclusion. The first part is the background and motivation. File scanning is a type of workload in which most file pages are only accessed once during each I/O stage. Sequentially reading or writing a file is the simplest file scanning. One main characteristic of file scanning is that the ratio of reused data is low. File scanning is common in data-intensive applications like scientific computing or AI training. They perform file scanning when loading initial data, doing checkpoint restarts, or visualizing results. On the other hand, kernel buffered I/O, the basic kernel file I/O mode, is commonly used for file scanning. For example, cutting-edge HPC clusters deploy the NVMe SSD-based burst buffer for I/O acceleration, and a recent burst buffer file system, HEDA-FS, used buffered I/O on the burst buffer node to access the NVMe SSDs. Although file scanning can hardly benefit from reused data due to the lack of data hotspot, buffered I/O can still benefit file scanning with the transparent buffering, data aggregation, I/O alignment, and prefetching enabled by the kernel page cache, and that's why buffered I/O is commonly used for file scanning. When the storage is not so fast, the kernel buffered I/O can exploit the device performance under file scanning. However, we found two performance issues when scanning files with buffered I/O on fast storage devices, especially on the upcoming next-generation NVMe SSDs. The first problem is the poor scalability with the device bandwidth. We perform a motivation test by aggregating up to 8 PCIe 3 SSDs to simulate storage devices with increasing bandwidth and formatting them with XFS. Then we generate sequential read and write workloads of a relatively large I/O size, 4 MB, using the FIO. As shown in the figure, as the device becomes faster, the buffered read performance improves no more than 35%, and the buffered write performance has no obvious improvement. As a comparison, we repeat the experiment in the direct I/O mode, in which the kernel page cache is skipped, and find that the direct I/O can scale better under such a large I/O size. Comparing the two experiments, we conclude that the kernel page cache does not fit for fast storage devices under file scanning. The second problem is the high interference from the background writeback to the foreground buffered writes. We demonstrate this by issuing sequential buffered writes to a large file. During the test, the application I/O bandwidth is stable at the beginning. However, as the 30 pages accumulate, the memory dirty ratio reaches a threshold and triggers the kernel background threads for writeback. The influence of device bandwidth is that as the device becomes faster, the proportion of software overhead increases during the writeback. This intensifies the software contention with the foreground buffered write, resulting in about 32% of performance degradation. To identify the parts that take major CPU time in buffered I/O software stack, we profile the CPU time breakdown of 3 workloads with Linux perf tool. These workloads are sequential reads, sequential writes, and sequential writes with active writeback. In the third workload, we manually set the dirty ratio threshold of background writeback to 0 to better manifest the influence of writeback. According to the profiling results, we can mainly get 3 conclusions. Firstly, we find that the page allocation takes major CPU cycles in all 3 workloads, with their proportions to be 33%, 36%, and 24% respectively. Deeper analysis reveals that file scanning has a low data reuse ratio, and each page cache miss needs to allocate a free page from the kernel page allocator. The high overhead of page allocation hinders the buffered I/O performance. Secondly, we find that background writeback increases the page indexing and dirty ring overhead a lot. File scanning has low data rewrite ratios, resulting in rapid growth of memory dirty ratios and triggering kernel writeback. The main issue is that the page cache index X array simultaneously maintains 30 states and 30 states of cached pages. Therefore, both inserting a new page and modifying the dirty states need an exclusive lock on the X array, resulting in intensive lock contention. Finally, data copy takes non-negligible parts of CPU time. However, as data copy between user and kernel space is inevitable in buffered I/O stack, this work does not optimize this part. Based on the above analysis, we built StreamCache to solve these problems. The key ideas of StreamCache are the batch updates of dirty states with decoupled stream-level index, and fast page allocation with sharded and file local free page list. StreamCache designs 3 key techniques to fulfill these ideas. Firstly, StreamCache designs a lightweight stream tracking module, which decouples the dirty states from the page index and maintains the dirty states in a separated data structure called STT. Secondly, StreamCache designs a stream-based page reclaiming module that can write dirty pages back while keeping interference to foreground I/O low. Thirdly, a 2-layer memory management module is designed to accelerate page allocation for file scanning. Now I will introduce each of these techniques in detail. The first technique is the lightweight stream tracking. It aims to maintain the states of the cached pages at the stream granularity. In this paper, stream refers to a range of logically continuous pages that are cached in the memory. To maintain the streams for fast lookup and modification, StreamCache designs a per-file tree called stream tracking tree. It indexes the streams of a file with their start page indexes. The rationale behind this design is that performing stream tracking in a per-file manner instead of in the whole system can better capture the file I/O patterns. Besides, indexing a stream with its start page index can keep the STT intact when the stream is extended. Each buffered I/O request is regarded as inserting a new stream. These new streams may need to be merged with the existing streams to keep them non-intersected. Each stream is represented by a stream descriptor. For example, in file A, assuming that the pages whose indexes are from K3 to N3-1 are cached in the memory, the stream descriptor will record a semi-closure interval K3 N3 for the cached pages. A stream is called a dirty stream if it contains at least one dirty page, and the descriptor will record the index of dirty pages with a dirty interval. Lastly, each stream descriptor maintains an upper limit field, which records the start page index of its following stream. It is used for the intersection detection in the following technique. StreamCache further designs a per-file stream pointer to optimize the stream tracking when the workload is mostly sequential. The stream pointer points to the stream that the last tracked I/O belongs to. This stream is also called the cached stream of this file. When a buffered I/O is tracked, the relative cached stream is firstly checked in case the new stream can be merged with the cached stream. If it does, the new stream can be merged without the need of STT searching. This case is also called the stream hit in StreamCache. To prevent the extended cached stream intersecting with its following stream, the upper limit field is inspected in each stream hit. The non-intersection condition is met if the end field of a stream is less than its upper limit field. The main benefit of stream pointer is that stream tracking overhead can be very low when the workload is mostly sequential. That is reasonable as sequential file I/O is common in file scanning. The main function of stream tracking module is to record the states of the cached pages, especially the dirty states. It differs from the existing methods in that the dirty states are decoupled from the page cache index and maintained at the stream granularity. For example, in the Linux page cache index X-array, each X-array node has a tag to indicate if any page in its subtree is dirty or under writeback. Maintaining such fine-grained dirty state requires an exclusive lock when manipulating each page. On the other hand, StreamCache maintains dirty states at the stream granularity, only requiring an exclusive lock for each I/O request. The stream pointer also decreases the tracking overhead on the sequential file I/Os. The second technique is the stream-based page reclaiming. It performs page writeback and eviction based on the STT stream descriptors, which can keep low interference to the foreground I/O requests. StreamCache designs two system-wide double-linked lists that connect all streams and the dirty streams respectively. Based on the global stream list, a pool of background reclaiming threads is kept to perform page writeback and page eviction at the stream granularity. Besides, while StreamCache does not maintain fine-grained writeback tags for the fsync commands as the kernel page cache does, instead it adds per-file writeback counters to denote the number of ongoing writeback requests. For example, if the reclaiming thread submits 1024 dirty pages for asynchronous writeback, it increases the writeback counter by 1024 atomically. In the writeback completion function, writeback counter is decreased atomically. The fsync command can return if all dirty pages in the target file are submitted for writeback and the writeback counter becomes 0. During the writeback, the reclaiming thread needs to refer to each dirty page for writeback. It involves two steps in StreamCache. Firstly, a range of dirty page indexes is extracted from the STT at the stream granularity. This only incurs an exclusive lock on the relative stream. Secondly, each dirty page is referred to on the X-array with its page index. In StreamCache, as the X-array no longer maintains dirty states, no X-array exclusive lock is required during the writeback. Writeback in StreamCache differs from the existing methods in that it changes the dirty states at the stream granularity instead of the page granularity. For example, the Linux page cache couples dirty states in page cache index. For foreground buffered writes, it needs an exclusive lock when inserting a new page or marking a page dirty. During the writeback, the writeback thread needs an exclusive lock when marking a page writeback or clean. This will cause intensive lock contention on X-array, resulting in severe interference between foreground buffered writes and background writeback. StreamCache, on the other hand, decouples the dirty states in a stream-based index. It only introduces minor contention as the dirty states are updated at the stream granularity. Besides, as the X-array does not maintain dirty states anymore, a writeback thread only needs an X-array read lock to get the pointer to a dirty page. When foreground buffered write coexist with the background writeback, this new index design changes the write-write contention to read-write contention on the X-array, and the X-array can handle read-write contention in a lock-free manner under its RCU mechanism. That's why the stream-based page reclaiming can alleviate the interference problem. The third technique is the two-layer memory management for fast page allocation. The bottom layer of StreamCache memory management module is a memory pool that consists of per-core memory regions. Each memory region pre-allocates a preset number of zero-order free pages and maintains them in double-linked lists. The top layer are per-file caches, which are file local list headers that store small numbers of free pages. Each opened file has a per-file cache, and its page cache misses will allocate free pages from its per-file cache. If a per-file cache runs out of free pages, it allocates from the memory region on the same core in a batch manner. The two-layer memory management module differs from the existing methods in that it not only shards the system-level free page list for concurrent-friendly page allocation, but also designs file local list headers for fast page allocation. Take the Linux page allocator as an example. It may introduce three overheads for page allocation. Firstly, free pages are maintained in different orders, and page splitting overhead is introduced when lower order pages run out. Secondly, pages of the same orders are protected by a spin lock, which ensures lock contention during concurrent page allocations. Thirdly, the kernel can be configured to clear the page on allocation, which will introduce extra overhead. In the two-layer memory management module, there is no page splitting overhead and only minor lock contention on multiple system-level free page lists. Besides, StreamCache removes page cleaning from the critical path. Finally, we find that adding per-file cache can boost the CPU cache locality of page allocation. It plays an important role in optimizing bandwidth-demanding applications like the file scanning. Now we have finished with the main techniques, and I will demonstrate the experimental results in the following part. This is our test bed information. We aggregate 8 Intel Optane NVMe SSDs into a RAID 0 array to simulate a next-generation storage device. Two baselines are compared in this paper, the original kernel page cache and the fastmap cache, which is adapted from the fastmap published on USENIX ATC 2020. All systems are integrated into XFS for buffered I/O tests. The tested workload covers both synthetic workloads and real-world workloads. The experiment in the paper tries to answer the following questions. How does StreamCache perform on real-world workloads? How does StreamCache perform with different workload parameters? And what are the effects of individual techniques in StreamCache? You can refer to our paper for more workloads and experiments. To evaluate how StreamCache performs on a real-world workload, we use the PF3D-IO kernel to test the buffered I/O performance. PF3D-IO kernel is developed by the Lawrence Livermore National Lab that writes checkpoint files in 6 different patterns of a laser plasma simulation application. We benchmark the PF3D kernel with both a small problem size and a large problem size. The results demonstrate that StreamCache can lift up the checkpoint bandwidth by 26% to 62% thanks to the stream-based page reclaiming and the two-layer memory management. By comparing the results of the two experiments, we can find that the average improvements under the large problem size is higher than that of the small problem size. This is because the large problem size triggers background writeback, and the stream-based page reclaiming can keep interference to foreground I/O low. Next, we evaluate how StreamCache performs under different workload parameters. We generate sequential reads and writes workload with FIO2. For each test, we alter the I/O size, total file size, or the number of processes that concurrently issue I/O requests. Experimental results show that file scanning can consistently benefit from StreamCache despite the workload characteristic. Finally, we use the PF3D-IO kernel under the large problem size as an example to demonstrate the effects of individual techniques in StreamCache. The results prove that all techniques in StreamCache can help to boost the performance of file scanning. That's all about our work, and now I will briefly conclude this talk. This work targets the problems of array lock contention and slow page allocation that hinder the performance of file scanning with buffered I/O on fast storage devices. Our key ideas are to separate dirty states from the page index, keeping them in dedicated stream-level indexes. And we design sharded and file local free page list for fast page allocation. 3 key techniques are devised to realize these ideas. Okay, that's all of my talk. Thank you very much.